In this video, we're going to be learning about a form of isomers that exclusively exist in alkenes, that being hydrocarbons that form a double bond. Now, if we analyze the structures of both of these alkenes, we can see, because each of them contain 4 carbons, and each of them contain a double bond in the second position, we can actually name both of these structures but-2-ene. Again, 4 carbons, double bond between 2 carbons in the second possible location, which in this case is between carbons 2 and 3. Now, the question that we can then ask is, are these different ways to represent the same molecule, or are they different molecules entirely? Well, the classic test about whether we're looking at an isomer or the same structure is, can we modify this structure, usually by bending the location of one atom into another position without breaking any of the bonds within the existing structure. If we can do that, we have the same molecule. So on the surface, it looks like we can take this carbon up here, carbon 1, and simply bend it downward into this empty space in order to give us the position down here. The problem is that this space is not actually empty because we're looking at a line structure. There is actually a hydrogen that is already here. And because the double bond basically prevents us from being able to rotate this around, the only way for us to get this carbon 1, down here in this position where the hydrogen already is to actually break this bond here and break the bond with hydrogen and actually flip the 2 atoms around. And if we do that, we would end up with the molecule in this position like this. But that's breaking our same molecule or not test rule, because we actually needed to break bonds in order to change the structure, which technically means these are isomers and not actually different ways to represent the same molecule. Now, because the parent chain is actually identical, both of these have 4 carbons and a double bond in position 2, these are a little bit more subtle than straight structural isomers, so instead we call these a form of geometric isomers, because the only difference between these 2 molecules is the geometry and orientation of specific atoms at carbon 2 specifically. Now, biologists have figured out a shortcut to identify which form is which, if we assume that the molecule is relatively simple and only contains carbon and hydrogen. So the way that this works, we position the double bond horizontally so that the double bond forms a flat line with the horizon, and then we bisect the molecule in half with a line of symmetry along the double bond like this. And what we're looking for on the right side and the left side of the double bond is to look for the longest continuous carbon chain in both directions. So here we can see that the longest carbon chain is up here. There's only 1 carbon, and there's no carbon chain down here because there's a hydrogen. And likewise on the other side, the longest carbon chain is 1 carbon here, and there's no carbon chain pointing up because this is a hydrogen and not a carbon at all. So here we can see that the longest carbon chains are actually on opposite sides of the double bond if we orient the double bond horizontally. This side is pointing up and this side is pointing down, hence they are on opposite sides. And in chemistry, the prefix that we use to indicate opposite is the prefix trans. So we would describe this as the trans isomer or the trans form of but-2-ene. Whereas here, we can see that the longest carbon chain on the right-hand side is still pointing up. But here, because the bonds with this hydrogen and carbon 1 have been switched, we can see that carbon 1 is also pointing up. So the longest carbon chains are now on the same side of the double bond if we look at it horizontally. And the prefix we use for same is the cis isomer. So, mentioned previously, cis and trans are common simplified forms that biologists use frequently in discussing fats. For example, cis fats are fats that have a double bond in the fatty acid structure where the longest carbon chains are on the same side of the double bonds, whereas the unnaturally occurring trans fats have the longest carbon chains on the opposite side of the double bond like this. However, once again, this nomenclature system is a little bit reductive because it implies that the molecule only has carbon and hydrogen, but as we learned in the previous video, it is actually possible to get a little bit more complicated when we start introducing things like halogen substitutions in. So in chemistry, the notation that we use is similar, but is a little bit more nuanced to include consideration of atoms that are not carbon or hydrogen. So, the way that we deal with this in organic chemistry is identical, at least in the beginning. We orient the molecule horizontally like this and then bisect the molecule using a line of symmetry showing the right and the left sides of where the double bond is. So, the next thing that we need to do is to find the two atoms that are connected to each of the carbons on the right and the left sides of the double bond. So here's a carbon on the right side, and this carbon is connected to another carbon up here and another carbon down here. And then on the left side, this carbon here is connected to a carbon up here and another carbon over here. Likewise, same thing. Carbon on the left side of this double bond connected to a carbon up top and a carbon on the bottom, and the same is true here. Nothing new so far. We can see the longest carbon chains are still visible here. Now, the next thing that we need to do, once we consider each of the carbons on both sides of the double bond, we need to look to the atoms that these carbons are connected to and find which atoms these carbons are connected to have the highest atomic number. What exactly does that mean? Well, this carbon is connected to another carbon that has the atomic number 6. And this carbon connected on the bottom is connected to another carbon, which is atomic number 6. And then likewise over here, so if we label all of these carbons as being atomic number 6, this is not traditionally helpful because we have a giant four-way tie either way. So next, we look at the atoms that this carbon is bonded to next, which in this case are 3 hydrogens here, and we know that hydrogen is the atomic number 1. But this carbon down here is bonded to 2 invisible hydrogens here, so again we have a tie, but then it's bonded to a bromine here, which definitely has a higher atomic number than hydrogen, and likewise this carbon here bonded to a bromine, definitely a higher number than hydrogen. And on the other side, again, we go to carbon, atomic number 6. Then there's a carbon here, atomic number 6. So we have a tie. So we go to the next atom that carbon is bonded to. Here we've got 3 hydrogens, but here we've got a chlorine that is definitely a higher atomic number. So once we find the side that has an atom with the larger atomic number, this is the quote-unquote dominant side that we're going to look for. So instead of simply looking for the longest carbon chain, we're going to go along each side of the double bond until we find an atom that has a higher atomic number than the same position atom on the other side here. So here it's bromine, so we would mark this as the dominant side as being down, whereas over here it would be up. Then on this side, again, we break the tie by going to chlorine, so this is our dominant side, so we would position this down, and here likewise the same. Now, just like with the cis and trans simplification, we can see that the atoms with the largest atomic number here are on opposite sides of the bond, so this is what we would call the E form of the isomer, or simply the E isomer, and here we see the atoms with the largest atomic number on the side chains off of the double bond are on the same side of the double bond, and this is what we call the Z isomer. Now, if we integrate these into the names, if we want to actually name these compounds, we can take one of these because these are identical otherwise in terms of side chains. The only difference is this designation here. So, in this case, our parent chain is going to be but-2-ene in both cases here, because that's the number of carbons of the parent chain and the position of the double bond. Then we can see here, we're actually going to call carbon number 1 here because bromine comes alphabetically before chlorine does. So we're going to say 1-bromo, and then we can see that on carbon 1, 2, 3, 4 is a chloro, and then we have a methyl on carbons 2 and carbon 3, so we have 2,3-dimethyl, which I'll need to squeeze in here, and then the only thing that we need to add in this name here is which form of the double bond geometric isomer we have. So because the double bond is in position 2, we would put in brackets here, double bond in position 2 is the E isomer, meaning that the atoms containing the largest atomic number element off of the double bond here are on opposite sides of the double bond. And since here they are on the same side because carbon 1 is here and carbon 4 is here, this molecule's name would be identical, except we would put 2Z, indicating these are on the same side of the double bond. So this would be called 2Z, 1-bromo, 4-chloro, and I'm going to have to make a little bit of space here, 2,3-dimethyl, squeeze that in there, but-2-ene. So, not surprisingly, the EZ distinction is the source of much frustration in organic chemical nomenclature, but once again, the analogy with cis and trans is basically the same, but instead of looking at the largest carbon chain, instead we're looking for an atom that has the longest or the largest atomic number that comes off of the double bond. To practice your identification of E and Z forms of geometric isometry, you can try the practice problems below, where the structure that you will have to name is one of the geometric isomers, either the E isomer or the Z isomer, and once you identify the correct name, see if you can draw the opposite isomer in the space provided to the right.